start off with, I'm going to show some notes here and I will pause briefly, but then the expectation is that you would actually pause your video so that you could have time to write these down. These notes should be handwritten, of course. Helps you remember them. So to start with, a force is a push or a pull, nothing more or nothing less. Please do not overcomplicate forces. It's just a push or a pull. It's measured with this tool we normally called scales. I'll show you a couple examples of those. The SI unit is the Newton.
188.
It's abbreviated. It's abbreviated with a capital N. Of course, it was after the fellow named Isaac Newton, and so that's why it's capitalized, I would suspect. And another common unit we see is pounds. And so I could show you here a spring scale. This is something that I got many years ago, I think at Harbor Freight. And you can see that, I don't know how well you can see this. This says pound, 50 pound, LB. And what happens is, as you pull, if I hold here with one hand, and I hold here with the other hand, we'll back out just a little bit. As I pull this way, you'll see the spring moves. Now you can't see this, but I'm putting a pretty good force pulling my hands apart here, and we can see that. We can actually measure that. So if I pull about this, that's a force of 10 pounds. I go up to here, that's 15 pounds. So we can measure pulls, and a common unit there we were seeing is pounds, of course. Another thing we can do is classic set of bathroom scales. This measures pushes. So if I take my thumb and I push down here on the bathroom scale, I can push with a force of 10 pounds and 20 pounds and 40 pounds. I don't know that I can do much more with that. We could see this weight right here. Now if you look at this is a 10-pound weight. If we set it on there, we might expect to see it to go up to about 10 pounds. Now, a force is a push or a pull. It's just a push or a pull. It's measured in scales, and the SI unit is the Newton. The unit you're most familiar with is pounds. We're going to circle back to this idea of pounds and newtons and forces and how it relates to weight in a minute. But first, let's review another thing about forces. This is something you need to get through your head and make sure you understand. A net force is the same thing as an unbalanced force. The words are used interchangeably. So net forces and unbalanced forces are the same thing. So an example of that might be if we looked at something like this, where we had a force going up and a force going down. Now we'll talk more about what this might be in a minute, but suffice it to say these arrows represent how hard something's being pulled. Well, these would be equal, and so here you would say that there is the net force would equal 0. So although there are forces on this object, there's actually no net force. So when we go back to here, a net force is the same thing as an unbalanced force. So if a net force is 0, then that of course means a force is balanced. So this would be an example of a balanced force or no net force. This would be an example of an unbalanced force, because you'll see here that this force is shown by this arrow is shorter, so therefore it's a smaller force than this force here that's shown by a longer. Now this is force normal, force gravity. We'll talk more about that in just a second. But you can see this actually does have a net force. This would have a net force, and it would be, we could quantify it, but for now you could just say, well, it would be downward. The force would be downward because this is bigger. So that would be a good example of a net force or an unbalanced force. And remember, these words are used interchangeably. That can get a little confusing. Now there's lots of different types of forces that we'll talk about in physics. Remember, don't overcomplicate this. It's just a push or a pull, but that push or pull sometimes comes from different things, and so sometimes we have names that we use here, and we commonly will use what I have here in black, as you just saw over here to quickly describe sort of the origin of those forces. And so the force applied, this is commonly used to just meaning something is pushing that doesn't really fit into these other categories. If you're pushing a person on a skateboard, well, you are providing the force applied. So it's pretty much the applied force would be something that doesn't fit into these other categories. 191. If perchance you happen to be on a large planet that was perfect for human life called Earth, you would always be in the presence of this thing called gravitational force. You can never, ever escape that as long as you're on Earth. So that's always there. And of course, that's shown as I did here with the force of gravity. It's always there. It's always pulling downwards. We'll talk more in a minute about a specific of the force of gravity, and that's often called weight. So remember, when we have scales here, what these scales are doing, they're measuring pushes or pulls, and specifically when you're standing on the scale, or I put this 10-pound, when I put this 10-pound weight on that scale, it was measuring the force of gravity on it. Normal force is actually the force that's always against. The normal force is always against the force of gravity. I don't know if you've noticed, but rarely do we fall towards the center of the earth. The vast majority of the time there is a normal force keeping us from falling. When that normal force is absent, we do things like fall, and we free fall, and we accelerate very rapidly downwards. And so when you jump off of something, you no longer have a normal force, so you're going to be going down and falling. And so the normal force is what's going against gravity. So again, we could go to back to our example here. This was the force of gravity. That normal force was equal, you would just not be falling. But if that normal force for some reason is less than the force of gravity, so in this case, the normal force is less. This might be an example of if you step into soft mud. Well, sure, it gives some force upward, but not enough. You're going to sink. And so that's an example where you would have a net force downwards. The friction force is something we see very commonly. This is a force that resists motion between two objects. We'll talk a lot more about friction later, but suffice it to say, if I was going to try to drag this 10-pound weight, although it weighs 10 pounds pulling downwards, I should be able to drag it for significantly less than 10 pounds. And this may be kind of hard to see, but earlier I was able to there we go. I don't know if you saw it. This would be the force that's resisting motion. Here I was able to pull this for a force of about 5 pounds. It moved. You're welcome to verify that by pausing it. But force of friction is a force that opposes motion. Air resistance, this is pretty much always present, as we've talked about in class. If you think about a piece of paper fluttering down or a feather, why does a feather fall slower than a brick? Well, in air, that air is always pushing up as something is falling downwards. So you could kind of think about it if we went back to this, force of gravity. And in this case, if we said, well, let's forget about that sitting on something. What if it was the force of air? So if you have the force of air pushing up as you're falling and force of gravity, well, that would be having an impact on as something falls. And the truth is, the faster something falls, the bigger this force actually gets. And so you could see there would come a point when the force of air resistance upwards would equal the force of gravity downwards. And at that point, the object actually goes from a place of having a net force on it downward to a net force of 0. And when that happens, when that net force becomes 0 because the force of air resistance is equal to the force of gravity, when that happens, we find ourselves in a state of, we would call that terminal velocity. And that's where air resistance equals the force of gravity. So as you can see, if the force of air resistance would equal the force of gravity, and in this case, it's important to realize the forces would be balanced here, and there would be no acceleration. It would just be moving at a constant velocity. We'll talk more about that a little bit later. Tension force and spring force are not something we're going to talk a ton about, but a tension force would be if it's essentially a force is a push or a pull. The tension force would be the measurement of how much pulling force is on something. A spring force would have to do if a spring is either pushed or pulled. The force that's on is considered a spring force. Honestly, in beginning physics, we don't spend a ton of time looking at these two, but we do spend a reasonable amount of time analyzing these 5 right here. One other distinction between forces is an idea of contact forces. Contact forces, and then of course non-contact forces. An example of this would be gravity. I think we all realize nothing's actually touching us, but we all have a pretty good sense of if you jump off a table, gravity's pulling you downwards. Nothing's touching you, but gravity is pulling. That would be an example of a non-contact force. Another example maybe that we can see easily is like with magnets. You can have non-contact where I can move this. Oops, and there it moved. I didn't actually touch it. It jumped across there. Magnets represent another area of non-contact forces. A contact force here would be if I was actually just touching it. So typically the applied forces, normal forces, frictional forces, air resistance force, these are all contact, and then the one that is non-contact would be the gravitational force. Another couple examples, sorry, just now realized that's not in the screen, non-contact. Another couple examples, as I already showed, we have gravity. Magnetic forces is something we'll talk about later, and electrical forces, those are primarily the non-contact. So Newton's laws describes objects and forces in very certain terms, and they're not that complicated to originally be aware of, but they do end up being, you can spend a lifetime really comprehending them and applying them. So the next video I'm going to start, and I'm going to explain in a lot more detail Newton's laws, but I will say in this video that Newton's first law is described as an object at rest stays at rest, and an object in motion stays in motion with the same speed in the same direction unless acted on by an unbalanced force. Another way of saying that in a little simpler terms, this might be 5th grade terms, is objects keep doing what they're doing in a straight line unless an unbalanced force acts on them. I could substitute the word net force in there instead of unbalanced force, because remember, they're the same thing. Newton's second law, again, the next video is going to have more details on this, but Newton's second law states that unbalanced forces always cause acceleration in the direction of the net force. Remember, unbalanced forces and net forces are the same thing. There's an equation, acceleration equals force over mass. It's most commonly written, and I would recommend just writing this in your notes as your equation, where your equations are force equals mass times acceleration. A lot of people struggle when there's fractions in an equation, and we can really easily get rid of it here. And then the third law, and again we'll talk a lot more about this in the next video, is for every action there's an equal and opposite reaction. This could also be said for every action force there is an equal and opposite reaction force. Thank you.